Hello, everyone, and welcome to this guest lecture on machine learning. Today, of course, we'll be talking about machine learning, and specifically, we'll be talking about two kind of types of machine learning, regression, and specifically lasso regression and ridge regression and elastic net regression, which is kind of a combination of the two. And we will also talk about support vector machines, which will be using those support vector machines. We'll be talking about it in terms of predicting dichotomous outcomes. So do you fall into one group or another group? First thing I want to mention is that machine learning, right, is a very big topic, and I'm not going to be able to go over everything today, of course. And so I wanted to point you to two courses at the University of Oregon that take more of an in-depth investigation into machine learning. And so the first course is EDLD 654 over in the education department. I looked at DuckWeb today, and it looks like it's going to be offered in the fall. So if you're interested in machine learning, specifically in R, because this class is all in R, I would highly recommend that class. The class covers things like penalized regression, which I'll be talking about today, k-nearest neighbor models, decision trees, bag trees, random forests, and neural nets. Neural nets, it really isn't a deep dive into neural nets, but this next class will actually does provide kind of more of a deep dive into neural nets. And the second class is Computer Information Sciences 510, this data science studio, which is in Python. And so don't worry if you don't really kind of know Python going into this class. The class really builds up from basics. You start with simple assignment, kind of manipulating data, and it works all the way up to these machine learning models. So this class is definitely not designed for only people who have good working knowledge of Python. And in this class, it covers k-nearest neighbor models again, naive Bayes models, and then as I mentioned before, it takes more of a deep dive into these artificial neural nets, kind of exploring different ways you can kind of implement artificial neural nets and different kind of features you can include in those models. So again, this is all to say that machine learning is a very big topic. I'm not going to be able to cover everything here, but these are two great courses on machine learning. But today we're going to be talking about two different types of machine learning, as I mentioned before. The first is a supervised classification model, and that is a support vector machines, right? We'll be talking about that. And we'll also be talking about ridge lasso regression, which is a type of supervised regression. Nice thing to know is that you guys all actually already know some machine learning. So for example, if you look up here, there's logistic regression. Last week during lab, I mentioned logistic regression is a type of machine learning, and you know a type of machine learning, you know logistic regression. Another one you know is principal components analysis, right? In dimension reduction, PCA is also a type of machine learning. Okay, so the first big thing to talk about with machine learning is kind of what the goal of machine learning is, running these machine learning models. So we can kind of think of this distinction between explanation and prediction. So most of the stuff we've done thus far in 613, 612, 611 is focused on this explanation, right? We are focused on these predictors, and we want to understand how these predictors relate to some outcome variable, right? We have our intercept, and then we have predictor 1, predictor 2, all the way through predictor n. And we're interested in saying, okay, what's the association between these predictors and our outcome variable? And can we infer something about the larger population from these values? And so since we're interested in that, we are very focused on, okay, what are our estimates and how accurate are our estimates, right? We want very accurate estimates because it makes it our explanations more accurate as well. In machine learning, the shift kind of moves to the outcome, right? We are most interested in predicting outcomes. We're interested in making some prediction. So we build a model on one data set, and then we apply it to another data set and say, hey, can we use this model that we designed on one data set? Can we use it to generate predictions on unseen data we've never seen before? Can we build a model that is able to make predictions in that data set? So the focus of machine learning is really on prediction. So I have a bit of an example here, right? Imagine there is a coffee shop, and you want to ask how much coffee will a person buy at the coffee shop? right? So with this explanation focus, you might ask, what is the association between how tired a person feels and the amount of coffee they buy? What is the association between how grumpy a person is and the amount of coffee they buy? What is the association between how old a person is and the amount of coffee they buy? So here we are really focused on kind of examining the antecedents, the causes of someone buying coffee, right? We want to see what causes someone to buy coffee. We're trying to explain that behavior. In contrast with our prediction, we say, can I predict how much coffee an independent set of customers will buy, right? So we're focused on predicting how much coffee a person will buy, not so much on kind of explaining why they are buying coffee. So to take more of a deep dive into this, this example, we might imagine that you go to location one, you go to one coffee shop, you find a Starbucks, you walk in and you say, hey, can I ask people how tired they are and then see what size of coffee they get, for example. So you might run this model at location one, right? And you might find that, okay, when a person has 0 tiredness, they're not tired at all, they buy about 5 ounces of coffee. And then for each one level of self-reported tiredness, they increase all the way up to being absolutely, completely tired. You see that for each additional step from 1 to 10, the tiredness increase, the amount of coffee they buy increases by 0.95 ounces. So right at around 6 tiredness, you're seeing people are buying slightly more than 10 ounces of coffee. And then you might go to location 2. And again, you're interested in kind of explaining how much coffee a person will buy. And you run another model and you say, okay, at this location, a person who is not tired at all, they score 0 on tiredness, they buy about 11 ounces. And then for each additional level of tiredness, they move up. The amount of coffee they buy increases by 0.64 ounces. So that's the kind of the traditional approach. That's more the explanatory, the inferential approach. The machine learning approach is a bit different. So the first step is the same, right? We go to location 1 and we create this model. We predict a person's coffee consumed from their self-reported tiredness. We find that right at 0 levels of tiredness, they buy about 5.04 ounces. And then for each 1 unit increase in tiredness, they buy an additional 0.95 ounces of coffee. So that's all the same as we did before with the inferential approach. The difference is that we then take that model that we developed using location 1, we call it training the model. We trained it on the data from location 1. And we apply it to location 2. So here's the location 2 data. And we're saying, okay, can we use this original model, this location 1 model, can we use it to predict how much coffee a person will buy at location 2, right? So here is our best fitting line at from location 1, predicting how much coffee a person will buy at location 2. So really to summarize, the goal of machine learning is to develop a model that is able to generate predictions at with a new data set. So we have a model trained on one data set, and then we apply it to another data set and see if we can generate good predictions. So the machine learning process can be definitely confusing at first. It definitely confused me the first time I was kind of exposed to it. So I think it's good to kind of map out the steps a researcher will go through when they are running a machine learning model. So the first step is to split your data, right? So you collect 1,000 observations. You're going to set some aside to create the model. So you might say 75%, 750 observations are going to be my training data. And then you're going to set some data aside as a testing set. And that's what you're going to test the model on. You're going to see, okay, can my model make good predictions when it's applied to a new data set? So in our previous example, you can think of this training data set as location 1 and the second data set as location 2. But in most cases, you're just going to collect a bunch of data. You're going to randomly sample from that data and split it into 2 groups. So you have your training data. You do this process, generally called cross-validation. You run these resamples. I'm not going to focus on that yet. We're going to talk about it later. So I'm going to kind of just wave my hands over this section and move on to the next section. Okay, so you have your training data. Then you want to create a model. You want to analyze your model, right? Part of this model creation process, you might choose your predictors. You say, okay, is there going to be an interaction? Maybe there's little features I want to tweak in my data. Should I center things? Should I run a PCA and combine some predictors? And so you're going to create this model. You're going to analyze it. You're going to evaluate it. Again, we'll also talk about evaluation in a couple slides, what I mean by evaluation. Then you tune your model. So you ran your first model, you evaluated it, and you said, okay, well, this model isn't doing as good as I thought it would. I expected to get 100% prediction, which is never going to happen, or almost never going to happen. But you hoped to get something close to 100%, and you got 50-50 prediction. And you say, okay, well, this is not really a good model. What I want to do now is I want to tune my model. So this is also called feature engineering. And this is when you kind of change your model to see if you can generate better predictions, right? You might say, okay, I'm going to drop this predictor. I'm going to combine these predictors. I'm going to tweak this little parameter, which I'll also talk about tweaking parameters later. But you're just going to change your model. And then you're going to, again, analyze your model, and you're going to evaluate it and say, okay, did it do better? Did it do worse? Maybe it wasn't as good as you thought it would be, so let's tune it again. And you're just going to keep doing this over and over and over until you get a model that you are happy with, that you think is a good model for generating the predictions. So once you've evaluated your final model, you say, it's okay, you have your optimal model. It is only at this point that you then use your optimal model to generate the predictions in the testing data. Up until this point, through this whole model creation process, you never, ever touch your testing data. Your testing data should be locked away. You should not use your testing data until you've generated your optimal model and you say, okay, I'm done creating my model. Now I get to test my model. The reason you don't want to kind of dive in or start working with your testing data set earlier is that the testing data, the results from the testing data are going to start influencing your model, your model creation process. So to say that you're taking kind of an independent model and generating predictions in new data, well, that's not really the case if you use that new data to inform the creation of that model to begin with. So again, you're going to split your training data and your testing data, and you're not going to touch your testing data until you've identified your optimal model. Okay, so we've split our data. We ran this resampling, which again, I'm just hand waving over. And then we want to run a model. But the question is, which method should we use? Which method should we use to run this model? As we saw in a previous slide, there's tens and tens of different methods, probably hundreds of different methods. Which one are we going to use to run our model? So that's our first question. And there's kind of three different considerations we can take into account when we're considering which method to use. One is whether the model is flexible or whether it is interpretable. So this is a trade-off between two different ideas. So a flexible model is going to provide very, very good predictions, right? It's going to be able to capture all the little nuances in the data. The downside is it's generally not going to be as interpretable, right? If you, for example, have a five-way interaction, could provide very, very good predictions, but it's going to be very, very hard to explain what that means. So this graph or this figure here just kind of shows some examples of methods that fall between interpretability and flexibility, right? So one method which we'll be talking about today, which is highly interpretable, is lasso regression, but it's not as flexible as some other models. It's generally not going to provide as good predictions as other models, but it's very kind of easy to explain what's going on with a lasso regression. In contrast, we'll also be talking about support vector machines, which can, kind of depending, be interpretable. But in some cases, if you're using these kernel functions, which we'll also be talking about, if you kind of really take the support vector machine to the max, you can get very good predictions, but it can be harder to interpret what's going on. And so you might ask, okay, what should I be focused on when I'm choosing a method? Should I be focused on flexibility or interpretability? And the answer, which no one likes, is, well, it depends, right? So in some cases, maybe you do want a very flexible model and you don't care that much about interpretation. So you could imagine a self-driving car, right? It's not really necessary for the people designing that to say, okay, well, the car recognized that that was a tree and that was a fire hydrant, and they decided to, the car decided to aim exactly 2 inches away from the fire hydrant and then scoot around the tree, right? So it's not that important that we're explaining exactly what is informing the predictions. It's just important that we are making sure the car stays on the road, is not hitting other people, that sort of thing. The other side is sometimes you do want more of an interpretability. So for example, if you design a model, right, and you want to write this paper on music preferences, right? You're predicting a person's music preferences from their personality traits, and you design this model, you use the personality traits as predictors, and you are able to predict with 99% accuracy whether a person will like a certain genre or not, right? And that's awesome. And then you bring it to someone else and you say, I developed this model, I got 99% accuracy. And they say, oh, that's great. I'm interested in personality traits, predicting music preferences. So kind of what personality traits were most important? What was the relationship between conscientiousness and a preference for a certain genre? And you say, okay, well, I don't know that. I used a more black box method. I don't know what's going on exactly inside the model, but I know I'm really good at making these predictions. Well, the person might say, okay, well, that doesn't seem that useful to me. I'm interested in the association between these personality traits and whether people like certain genres. I'm less interested in just seeing whether I can predict with 100% certainty whether a person likes a certain genre or not. So in that case, you'd probably want a more interpretable model, but also one that is going to be necessarily less flexible. Oh, so this is just a kind of another way of showing a difference between interpretable and flexible models, right? This figure over here is very interpretable. You get a flat plane, but we see that we kind of have these larger residuals here. We're not making perfect predictions. In comparison, we can have this kind of smooth plane that has very, very low, small residuals, right? It's generating really good predictions, but it's going to be much harder to explain what exactly is going on in this model, right? So you would have to, trying to describe what is going on right here, this little bump right here, is going to be hard. It's going to be less interpretable. So that's one thing to take into account, the flexibility versus interpretability of a model. Another thing to take into account is whether you are going to create a supervised model or an unsupervised model. So the idea here is that with a supervised model, you have the correct answers in your data set. So if we think back to running our logistic regression models last week, right, in lab, we were predicting whether someone reported harassment or not. Well, in the supervised method, which is logistic regression, we have whether they actually reported harassment or not. So we have one column, which is our predictions of whether they reported harassment or not. And then we have another column, which corresponds to whether they actually did or did not report harassment. So with the supervised method, we can essentially check our answers, see whether our answers are correct. We have the actual results in our data set. Same thing with linear regression, non-logistic regression, right? We have the actual Y values. We're predicting the Y values, but we also have the actual Y values to see how far our predictions are away from the actual values. In contrast, an unsupervised model does not have the kind of true values within the data set. So we can think of principal components analysis, right? It's when we run a principal components analysis and we conclude, okay, component 1 has 3 items, right? Item 1, item 2, item 3. There isn't really a way for us to say, okay, well, there's truly one component that includes these 3 items, right? We're using a mathematical method to try to create those components, but we don't know whether, okay, do these items actually truly map onto this one component, and we label this component happiness. Is this truly a happiness component? Can we check whether item 1, 2, and 3 are actually exist in this happiness component? Well, no, we can't. So that's an unsupervised method, right? We don't have the answers in our data set. So here's 2 examples. Over on this side, right, we are running what looks like a support vector machine to me. where we have these two different colors, right, for class 1 and class 2. And we are able to say, okay, everything on this side should be categorized as class 1. And we can actually see, okay, well, these values are actually class 1. So it looks like we're making accurate predictions. On the other side, we say, okay, everything to the left-hand side of this line are class 2. And we can see that they are actually class 2. And so that would be a supervised method because we have the true answers in our data set. On the other side, it looks more of a cluster analysis, and we're saying, okay, these data points seem to be similar to each other, so we're going to call this group 1. These data points seem to be similar to each other, so we're going to call it group 2, and then group 3, group 4, group 5, right? We have 5 clusters, but we can't really check, okay, are these values truly a part of a group 1, and are these points truly a value of group 2? In reality, really, we're just saying, okay, these observations are similar to each other, so we're grouping them together, but we can't really prove, we can't really show that these values actually belong in this cluster. So that's the difference between unsupervised and supervised. Unsupervised, you don't have the true values in your data set. With supervised methods, you do have the true values in your data set. Then we can also talk about regression and classification. And this terminology is a little unclear because, right, when we run logistic regression, we're actually running a classification model, right? We're classifying people into one group or another group. In the context of machine learning, this is often referring to whether your outcome is a continuous variable, right? 1, 2, 3, 4, 5, etc., or whether it is a dichotomous or polytomous variable. So is there 1 group, 2 group, 3 group, 4 group, 5 group, 6 group, etc., right? So that's the big difference. One is a discrete variable classification, and one is a continuous variable. So here's just a figure showing that difference, right? Here we're showing the relationship between gene 1 and some outcome variable. We're getting a linear relationship in this case. And then over here, we're running a classification model using these 2 genes as predictors and saying, okay, everything over here seems to be a diseased patient, I believe. And then everyone over here is a healthy patient. So one, we're grouping people, and the other one, we are predicting some value. So which method should we use? Well, we can think about the coffee shop example. What method would we want to use for that coffee shop example? So we can start over here and we can ask ourselves, okay, do we have, it says samples here. Really just think of observations. Do we have greater than 50 observations? And specifically 50 observations in the training set? If we say no, the answer really is get more data. Machine learning requires a lot of data. So if you're trying to run it on 50 samples, that's going to be tough. So if you have less than 50 samples, I advise you to get more data. Then we come over here and we have our next question is, are we predicting a category? Well, no, in this case, we're predicting how much coffee a person is going to buy in ounces. So that's a continuous variable. So we say no, and we are predicting a quantity. Say no, and then we ask, are we predicting a quantity, right? And if we say no, we're just looking, right? We might go to dimensionality reduction. But in this case, we are predicting a quantity, right? We're predicting the quantity of coffee someone is going to drink. And so we land in regression. Right now, I'm not going to dive into these kind of different methods because I'm going to talk about that later in this lecture. But for now, we know that we want to run some sort of regression model. We don't want to run a classification model, a clustering model, or a dimensionality reduction model. We want to run a regression model. Regression. Okay, so we've chosen a model and we can analyze our model. And then we have to ask, okay, how do we evaluate the model? And there's many different ways to do this. Last week, right, we talked about accuracy. We ran those classification tables, saw how many correct yes predictions we made, how many correct no predictions we made. That is one perfectly fine way of assessing model fit, right? How good is your model at making these classifications? In this case, for this regression model we're going to be running, generally, probably the most popular method for assessing model fit is to either use the mean square error or the root mean square error, right? So we take the difference between the actual values and our predicted values, square them, sum them up, divide them by n, and you get your mean square error. So mean square error, the units can be interpreted in terms of the original units squared, right? So this would be ounces of coffee squared, for example. And then with the root mean square error, we just take the root. And so that can be interpreted in terms of actual ounces, so not squared ounces. So mean square error, you get ounces squared. Root mean square error, you get just ounces. So in terms of assessing our model, right, we want to minimize mean square error on the test set, right? We want to have as few differences between our predicted values and our actual values as possible. Before we talk about evaluating our test set further, it is important to talk a bit about overfitting, which you've heard of overfitting, you're familiar somewhat with overfitting, but it's a really important concept, especially in machine learning, right? So we can have an underfit model where we are essentially missing the underlying relationship in our data, right? The model we have is not accurately representing the underlying relationship. So that's an underfit model, right? Our model is not an accurate fit to the underlying relationship. And then we might have a good fit model, right? Our model is an accurate kind of representation. It accurately captures the underlying relationship in our data. So that'd be a good fit model. And then we can also have this overfit model, right? In this case, we are capturing not only the underlying relationship, but we're also seeming to nearly capture all of the little variations, all of the idiosyncrasies in our data set. And essentially the problem here is that we are predicting noise in our data set, right? We are going to generate perfect predictions, near perfect predictions in this data set, right? With all of these different polynomials, we're going to produce almost near perfect predictions. But especially in machine learning, this causes an issue when we try to take that model and apply it to a new data set. So here is an example of what kind of the issue with overfitting is. Okay, so on the left-hand side, right, we have our actual function. This kind of curved shape here is our actual function. We have this good fit function, this blue one, which seems to be accurately representing the curve of that actual function. Then we have an underfit model, which seems to be missing the actual underlying relationship of the model. And we have an overfit model where our model is not only explaining the underlying relationship, but it's also explaining all of those little variations in our data set. And so you might say, okay, well, I'm interested in maximizing prediction. And so I don't care if it's overfit. I want it to maximize prediction. I want to capture all of those little variations in the data set. That is what I'm focused on. I'm focused on prediction. I want to predict every little difference in the actual data, right? That's a reasonable thing to conclude. The problem is when we apply this to a different data set. So I think this figure over here does a really good job of illustrating this point. And so we can focus on the first coffee shop, location 1 coffee shop, for example. Well, when the model is underfit, it has kind of large mean square errors, right? We're not capturing the underlying relationship. We're making bad predictions. So we have more residuals, we have more error. And so when we are underfit, we are producing, right, inaccurate predictions. Then we get to the good fit model and our mean square error goes down, right? And that makes sense, right? Our model is generating good predictions. We have very little residuals between our predictions and our actual values. And so the mean square error went down. And we can continue increasing the flexibility in the model and get to an overfit model. And we have a great model, right? Our mean square error is much, much smaller than it was before. And so we might say, okay, I want to go with this overfit model, right? I'm generating really good predictions with it. The issue is that, right, when we bring that model and apply it to another data set, overfitting to the specific data set, overfitting to the variation, the specifics of one model is going to result in worse prediction in the other model, in the other data set, right? So you're taking a model that is able to explain the actual variation in one data set plus all of the noise in the data set. And then when you apply it to the second location or you bring it to the second data set, it's again able to potentially predict some of that underlying relationship, but it's also going to be predicting all this noise that was in the first data set, which actually causes your mean square error to go up. So this difference is often called the bias variance trade-off. And the idea is that your expected test mean square error is going to be a combination of your bias, which is how poorly your model approximates the data or the underlying relationship in the data, plus variance, which represents essentially how poorly your model generalizes to another data set, plus some error. So here are some kind of definitions, kind of more formal definitions, right? Bias is error introduced by approximating a complicated relationship with a simple model, right? So that would be a underfit model. And then variance, where did it go? Variance is the amount by which model would change if we trained it on a different training set, right? So that is this difference here. That's the issue that we're running into. Variance is the issue we are running into. So as we keep overfitting the model, we keep adding flexibility to the model, our variance is going to increase in this case. So, right, either bias or variance can increase your expected test mean square error. So essentially you want to identify a method or you want to identify a model that has low bias, but also has low variance at the same time. So this figure over on the right here is essentially showing where would be the best model to represent our data, right? So as the flexibility increases, the bias is going to go down. We're going to get better and better fit until the point where we start overfitting and our bias doesn't decrease that much. And as we are overfitting, our variance is going to go up and up, right? We are going to start predicting noise in our training data set, and we are going to generate worse predictions in our testing data set. And so this mean square error U-shaped here, this mean square error line, which is a U shape here, is essentially representing how our mean square error changes over the flexibility of the model. And ideally, we would select the model that has the least amount of mean square error as a function of both bias and variance. So we want to pick a model that is just about here. And so you might ask, okay, well, how do we minimize test error without looking at the test data, right? Earlier, I said, don't touch your test data, lock it away. Don't touch it until you've chosen your absolute best model. Well, if you can't look at your test data, right? How do you evaluate whether it's a good model or not? And how can you see whether it has high variance or low variance? If you're only ever training your model on one data set, well, you're probably going to get high bias because you're going to keep fitting it to that one data set, and you're going to get low bias because you keep fitting it to that one data set, right? You're eventually probably going to overfit it to that data set, and you're going to have high variance because you've overfit it to that data set, you bring it to your test data set, and then your model is trying to predict all this noise, which doesn't exist in the same way in your test data set, and you're going to generate poor predictions. You're going to have high variance. So how do we minimize test error without looking at the test data? Well, one very, very popular method, which almost all machine learning methods use, is resampling. And so this is kind of a complex idea. It's intuitive when you become more familiar with it, but the first time, at least the first time I was exposed to it, there was many different levels to it, and it took me a little while to get my head wrapped around the exact idea of what's going on with resampling. So the idea, in kind of the simplest terms, is that, right, you have your training data set and you have your testing data set. You have this macro training set and you have your testing data set. Within the training data set, right, so this is the data set we are training the model on, we are going to take different resamples of that training data set, right? We're going to take different parts of that training data set and split it up in different ways, right? So for resample one, we're going to say, okay, some of this training data set is going to become the analysis data set, and then some of this training data set is going to become the assessments data set. And then for resample two, we say, okay, some of this data, again, is going to become part of the analysis data set, and some of it is going to become part of the assessment data set, and so on and so forth throughout our different resamples. And so the idea here is that for each of these different resamples, you're going to have different portions of the training data in your analysis set. So you're going to be training your model on different aspects of the training data set. And by doing that, we're going to essentially be able to see, okay, well, one, does this model trained on this analysis set, does it generate good predictions of this micro test set, this assessment set? And then we can say, okay, well, what if we train the model on a different portion of the data? Does it also provide good predictions in this different assessment set? And so in this way, we can kind of stop ourselves from trying to overfit to the data because we have different aspects of the data in each of these sets. We decrease, and in doing so, we decrease the variance, right? We're less likely to overfit to the data. And as a result, we are less likely to have variance in our data. So we're more likely to have generalizable models. Okay, so take the testing data set and we split it into resamples. And then you say, okay, well, how do we split it into resamples? Many, many different methods for splitting into resamples. One method is this leave one out cross-validation. And the idea is that you take how many ever observations you have. So in this case, we have 10 observations. Want to highlight, do not run a machine learning model on 10 observations. This is just for illustrative purposes. But we have 10 observations and we say, okay, 10 observations, we can create 10 folds. And so fold, you can think of a fold as just a kind of another word for a resample, right? So before we had resample 1, resample 2, resample 3, etc. In this case, we are going to have these different folds. And so with leave one out cross-validation, we just leave one out for each of those folds. So in fold 1, we take participant 1, they become part of our assessment set, and everyone else is in our analysis set. For fold 2, we take participant 2, they become part of the assessment set, everyone else is in the analysis set, and so on and so forth, right? We do that through all 10 folds. So we have quite large analysis sets and assessment sets made up of one person in each of these cases. So the problem with this method is that, right, most of your data is always going to be in the training set, so you might end up actually overfitting your model in this case, right? 90% of your data is in the analysis set, or let's say you had 100 participants, if 99% of your data is in the analysis set, well, your model is going to be pretty tied to that analysis set, even though you're running multiple folds. So another option is k-fold cross-validation, and there's various different types. K-fold cross-validation, I show a illustration of 5-fold cross-validation here, but I think the most popular is 10-fold cross-validation, and that's what I most often see being used in terms of machine learning. But essentially, the K in k-fold cross-validation refers to how many resamples you make or how many folds you make, right? So in 5-fold cross-validation conducted on a data set with 10 observations, we say, okay, we're going to have 5 folds, and that means 10% of the data is going to go into the assessment set, and then so I did that backwards. 20% of the data is going to go into the assessment set for fold 1, and 80% of the data is going to go into the analysis set for fold 1. Then you go to fold 2, and again, you take 20% of the data and put it in the assessment set, and 80% of the data and put it in the analysis set. So again, 5-fold cross-validation is less common than 10-fold. That seems to be kind of one of the gold standards, but this is just to illustrate cross-validation. Here is an example of the 10-fold cross-validation. So in a data set with 10 observations, you're actually going to get the same as a leave one out cross-validation. And so you can think of leave one out cross-validation as just a special case of k-fold cross-validation. It's a special case where the K just refers to the number of observations in the data set. So if you have 500 observations in the data set, you would have 500 folds, and that would be the same as 500-fold cross-validation. So that's k-fold cross-validation. There's also Monte Carlo cross-validation, which I see used less often, although it's very, very popular with running simulations. And the idea here is that, again, you might have, for example, 5 folds, and you again, choose 80% of the data to go into the analysis set and 20% of the data to go into the assessment set, but you allow the data going into the assessment set to appear multiple times across the fold, right? So if we look at the 5-fold cross-validation, observation 1 and observation 2 is only ever in the assessment set once, but with Monte Carlo cross-validation, participant 2 is in the assessment set twice, and participant 1 is actually never in the assessment set, right? But we see these repeats here. Observation 2 is in fold 1 and fold 4. Observation 6 is in fold 2 and fold 5. And then observation 8 is in fold 2 and fold 3. And then kind of the final method we'll talk about is bootstrapping. And again, I'm based off of our discussions last term. You're probably familiar with bootstrapping, but to again give a refresher on what bootstrapping is essentially we'll choose a number of bootstraps to run. In this case, we're doing running 5 bootstraps. And for each of those bootstraps, you randomly select some of the data to be in the analysis set with replacement. So the same participant can appear in the analysis set twice. And then you also randomly select some of the data to be in the assessment set. So the difference between kind of the K-fold, actually the difference between the Monte Carlo cross-validation is in the Monte Carlo cross-validation, a given participant cannot be in the same fold more than once. Whereas in the bootstrapping cross-validation, the same participant can be in the same fold more than once. So for example, participant 4 was in the first bootstrap, the first fold 3 times. So that's the kind of primary difference. And one final thing to note here is that bootstrapping as compared to K-fold cross-validation, bootstrapping will tend to have more bias, but less variance. Right. And the idea is that since we are including less of the data in the analysis set, we're going to generate less accurate predictions in each given fold, but we're going to tend to have less variance because, again, we're less likely to overfit to any given set of the data. But one nice thing about bootstrapping is that once you get when your sample is large enough, you start to see less bias as well. So you can kind of maximize having less bias and also less variance at the same time. So bootstrapping can be one very powerful method. Okay, so that is one way to minimize test error without looking at the test data, right? We resample the data, and that allows us to essentially run or identify a mini training set, run a model on that, and identify a mini test set and run a model on that. And you do that multiple times. You average maybe the root mean square error together, and you say, okay, well, how well is our model performing across all of these resamples? So that's one method, and it's useful, right? Because it allows us to not touch our testing data set, which again, we don't want to touch the testing data set until we're absolutely certain we are finalized with our model. We've identified our optimal model. Another method is called regularization, or also called penalization. And the idea here is that we are essentially going to penalize our model. We're going to add a little penalty to our model if our predictors or our coefficients get too big, right? So as our one of our predictors gets larger and larger, we say, okay, that might be great. It might be providing very good predictions in this data set, but it's unlikely it's going to be that large in another data set. So let's add a little penalty to it and not allow it to get as large in our data set. So we're adding a little bit of bias. The idea is we're adding a little bit of bias to decrease potential variance, right? Add bias, decrease variance. So one popular method is called ridge regression. And over on this side, right, we see that we are essentially calculating our residual sums of squares. And we are adding this penalty, this ridge regression penalty. And the idea here is we're taking the sums of the squares of the coefficients and adding that to the residual sum of squares. And we're also multiplying it by this lambda, which I'll kind of discuss in a bit. But we're adding this penalty, which says, okay, we are only going to settle on a model which has larger beta coefficients if we also see a corresponding decrease in the residual sums of squares. So it's saying that don't allow the beta coefficients to increase if we don't see a corresponding decrease in the residual sums of squares. And this lambda here determines how much of a penalty we are adding. So if this is 0, right, it's just a normal ordinary least squares regression. We're not adding any penalty, but you can also increase this to essentially infinity. At infinity, all your predictors are probably going to be 0, so it's not going to be that useful. But when you are tuning your model, right, I talked about earlier about feature engineering, you're tuning your model, you create one model, you kind of mess with it to see if you can make it better. Well, this lambda is one of those values you can mess with, right? You can run one model and say, okay, in this model, I'm going to include no penalty. The lambda is going to be 0. In this second model, I'm going to make lambda 0.5. In this third model, I'm going to make it 1, and so on, right? So there, you can kind of identify what the best penalty is for predicting some outcome. So that's ridge regression. And as we can see from the standardized coefficients, as the lambda goes up, all of our predictors start to shrink towards 0. I think they eventually, maybe they never exactly get to 0, but they shrink closer and closer to 0 as lambda increases, right? We see income drops, we see whatever limit is drops, we see rating drops, and we see student drops. Everything is pushed towards 0. And so in this case, as lambda goes up, right, our bias eventually does go up and up. It seems to be, where are we, about here? Bias starts to, this point, bias starts to increase. But from the beginning, variance starts to decrease. So again, right, we're adding a little bit of bias to decrease the variance. And so the optimal model would be right here. It'd be whatever this lambda is. So that's 1,000 and that is 10. Who knows what that is, but it's somewhere in it. Maybe that's 100 and something, 110, could be. But right, we are running on multiple models, identifying our best lambda value, and you might be able to identify, okay, I found the perfect lambda value for adding a little bit of bias, but also decreasing variance so that my model is more generalizable than it would be otherwise. Another method you can run, another type of regularization, is this LASSO regression. It's least absolute shrinkage and selection operator. And the idea is very, very similar to the ridge regression. We're also adding this little bit of bias, this little penalty for having large beta coefficients. The really only difference is that instead of squaring the coefficients and summing them up, we're taking the absolute value and summing them up. And again, right, we have our lambda, so we can include different levels of this penalty when we are kind of designing our optimal model. Some model, you could test whether having no penalty is a good model, a 1 penalty, a 100 penalty, and so on and so forth. And so the primary difference between the ridge regression and the LASSO regression is that with the ridge regression, the coefficients will shrink towards 0 and never really become exactly 0. Difference with LASSO regression, things will just plummet to 0, right? We see that whatever this was, I think that was income, it just starts shrinking and shrinking, red starts shrinking, shrinking, yellow starts shrinking, shrinking, and they hit 0. So in some cases, this is incredibly useful. And it's specifically useful because it provides very interpretable models, right? So if we go back to the ridge regression model, right, we are going to have generally, in comparison to the LASSO regression model, we're going to have a flexible model, right? We have our multiple predictors in there, we're generating our predictions, and it's going to potentially produce better predictions than the LASSO regression model. But again, we have multiple predictors, so it's kind of harder to interpret what the model means, right? It's a less interpretable model. In contrast, a LASSO regression model makes things plummet to 0, and then you end up with a more parsimonious model, a more interpretable model, right? So if we, for example, took a value of 3,000, a lambda of 3,000 or a lambda of 4,000, we're only going to have one predictor in our model. So it's going to be very interpretable, potentially not going to be creating as good of predictions, right? It's not going to be as flexible as a model using that terminology, but it is going to be very interpretable, right? One predictor, quite straightforward to interpret. And also, if you're running into issues with multicollinearity, right, dropping out predictors is going to get rid of that issue. It's going to solve that issue. And so as we can see, ridge regression has some benefits. Lasso regression has some benefits. Well, is there a way that we can kind of combine these two benefits together? Can we get a model that has some of the benefits of the ridge regression and some of the benefits of the lasso regression? And the answer is yes. Otherwise, I wouldn't have asked that question, of course. The model that combines both of these benefits and potentially weaknesses is called the elastic net as an elastic net model. And we can see that, right, we have a residual sum of squares and we're adding the ridge regression penalty, but we also add the lasso regression penalty. And we can also see that these lambdas are different. We don't have to have the same lambda. So in this case, we could again run a bunch of models and say, okay, how's our model doing when the ridge regression penalty is really small and the lasso regression penalty is very large? And then we can run another model and say, okay, how's our model doing when the ridge regression penalty is very large and our lasso regression penalty is very small? And then we could have run another model and say, okay, what if they're both at moderate levels or both at high levels, both at low levels? So elastic net is just it is combining both of these two penalties to try to identify a model that has kind of the desirable features of both ridge regression and lasso regression models. And a question I got asked last year when I gave this talk was, okay, so if elastic net can become both a ridge regression model and it can become a lasso regression model, right? If this lambda goes to 0, then we have a lasso regression model. And if this lambda goes to 0, then we have a ridge regression model. So why wouldn't we just always run an elastic net model? And the answer is that it costs us in terms of interpretability, right? We have two penalties. And so if we're trying to explain these coefficients to someone, we would not only have to say, okay, well, we added a ridge regression penalty, but we also added a lasso regression penalty, and we included 0.8 of this penalty, and we included 10 of this penalty. And so it makes it much harder to interpret what exactly our model is doing. So that is one potential reason you wouldn't want to run elastic net model. Okay, that concludes our discussion of regression, right? Predicting continuous outcome variables. We can now move on to discussing classification, right? Predicting membership in certain groups, predicting discrete variables. Okay, so we have our machine learning modeling process, right? We've split our data. We've ran a bunch of resamples, or we created a bunch of resamples. And then we can also, in this case, we are going to have to choose what method to use. And since our outcome variable is not continuous, it's discrete, well, we will have to use a classification method. And so again, many different types of classification methods. For this lecture, we're going to be talking about support vector machines. So this is a type of supervised method, right? We know the true answer, and it's also a classification method, right? We're predicting a discrete variable. So in my readings, or at least in my work, I don't come across support vector machines that often, but I poked around on Google Scholar, and it seems to come up a lot in neuroscience journals, journals about bioinformatics. So it's a very good thing to know, especially if you are doing work in those areas. Okay, well, yes, we covered regression. We're moving on to classification. So support vector machines might sound super advanced, but the kind of fun underlying idea, I think, is very intuitive. So we can look on the left-hand side of the slide here, right? And we see that we're seeing a relationship between a person's income, standardized in this case, and the size of the lot that their house is on, also standardized, right? So income down here, greater income as we move right, and then greater lot sizes up here, larger lot sizes as we move up. And we can use that information to predict whether someone owns a riding lawnmower, for example, right? So if someone has a lot of money, well, they're going to be more likely to buy a riding lawnmower than someone who doesn't have any money, right? makes sense. And someone who has a very large lot, right? They have acres and acres of grass. Well, they're probably also going to be more likely to buy a riding lawnmower than someone who lives in an apartment, right? They have their lot is essentially negative size because there's multiple apartments on the same kind of lot space. So someone who has a very low lot size or a very small lot size, well, they're also going to be less likely to own a riding lawnmower. So the idea with the support vector machine is that you try to find a plane. So I can find a piece of paper here, right? You try to find a plane, essentially a dividing line that best distinguishes between these two groups, right? So you have the yes group up here, you have the no group down here, and you're trying to find the plane, or in this case, a line that best divides those two groups from each other, right? So in this case, on this model, if we drew the line wherever any of these three lines are, we'd say, okay, everything to the left-hand side is going to be a no. We're going to predict a no. And if you land on a right-hand side, we're going to predict a yes. So we take this model, we apply it to a new data set, and we say, okay, if you are right on the left-hand side of the line, you're a no. If you're on the right-hand side, you're a yes. And we can also see that, right, there's multiple different ways of kind of estimating where this line is going to be. So one of the most popular is called a hard margin classifier, right? You're making a very kind of stringent margin. It's very hard margin. It's also called optimal separating hyperplane, right? Whereas the hyperplane that optimally separates these groups, that's kind of the idea behind a hard margin classifier. And so you choose the hyperplane that is farthest from training observations. And so what happens here is you can imagine drawing a line between all members of one group, right? This is supervised, so we know what group people are actually in. Drawing a line between all members of that group, and then drawing a line between all the members of another group. And that's called a hull, right? The line that surrounds them is called the hull, like a hull of a ship, like H-U-L-L. It's the hull of a ship. You have this line around it, the hull for the no group, a hull around this other group, the hull for the yes group. You identify the closest points on those two hulls. You draw a line between it. This dotted line right here is that line between it. You go halfway along that line, and then you find a perpendicular line, and that becomes your hard margin classifier. So you take this model, you've identified where the plane is, go to another data set, and then you test whether, and then you test it on the other data set, and you say, okay, everyone on this side of the line is going to be yes, everyone on this side of the line is going to be a no. Has some downsides. One of those downsides is that it's sensitive to outliers, right? So we can imagine we have this data set here. We don't necessarily know whether this is an outlier. We'll call it an outlier, but it could be a legitimate observation. But let's say we add this observation here. We get this new observation, which is somewhat farther away from the no group, but we know that this observation is a no observation because we have the true answers in our data set. Well, if we put a new point here, our hard margin classifier is going to be drawn right here. It's going to be drawn between the two groups. And if you're really focused on predicting the data in your training group, well, you say, or your training data set, this is great, right? All of the points on the left-hand side, those are all still in the no group, and all the points on the right-hand side are still in the yes group. So we're making perfect predictions. This is great. The downside of that, right, is that we are potentially overfitting the model again. We are overfitting the model. And so we can imagine that, let's say we apply this to a test data set and we get a point right here. Well, according to this hard margin classifier, a point right here, right, just slightly to the left of this hard margin classifier, that's going to be predicted as a, that is going to be predicted as a no. But just looking at it, just kind of, if you were to take your best guess, you'd probably say, well, that looks far more like a yes. It's much closer to the other yeses than it is to any of the no's. So potentially in this case, we're overfitting to this testing data set which is causing worse predictions when we get to our training data set, because our hard margin classifier is thrown off because of this one variable, this one observation, which might be an outlier. So kind of a solution to that is to use what is called a soft margin classifier. And the idea here is that we essentially allow more points to be on essentially the other side of the plane. So with what we call a C, so this is another one of those hyperparameters that we can vary from model to model to try to identify the best fitting model. This C, when it is 0, we're essentially saying, okay, use the closest points to each other to create that hard margin classifier. And then we can slowly say, okay, well, don't use the closest points to each other, use the second closest points, use the third closest points, and you move out and out. And so essentially you're allowing this plane to kind of approximate the difference between the groups rather than kind of having to accurately or specifically be stringent at splitting these two groups in half. So with this C equals 0, we're saying, okay, I'm going to have a hard margin. Everything on this side better be in this one group. Everything on this side better be in this other group. And with a C of infinity, we say, okay, well, let's go to the farthest points, draw a line, and we're allowing some kind of misclassification in between. So presumably, in most cases, the optimal hyperparameter for C is not going to be, or the optimal value of C is not going to be 0. Probably also not going to be infinity, but it might be somewhere in between. So again, we can think of this as adding a little bit of bias to our model to decrease the potential variance when we go to apply this to a new data set. So that's one of the downsides, sensitive to outliers. Another downside is it fails when there isn't a hyperplane that perfectly separates the two groups, right? We see this data set over here, and we're kind of stuck with our plane, right? Here's our flat plane. You can imagine it as a line, right? How are we we can't really split this group, right? Ideally, we would curve it into a circle, select everything inside to be a yes and everyone on the outside to be a no, but we aren't allowed to do that. We have to use a plane. So what can we do? We can use these kernel functions. They're also called kernel tricks, which I think are really, it's a really kind of cool idea. And the idea is that you're taking this feature space, right? Here's our original feature space, which we can't draw a circle in. We can't really figure out where to put a line. Well, we enlarge that feature space potentially if it's 2-dimensional to begin with. We enlarge it into 3 dimensions, and then we are able potentially to draw a hyperplane, a flat hyperplane between our two groups, right? So we can imagine in this 3D feature space, we're pulling all the values up, all the yes values are at the bottom, all the no values are up above, and then we're able to slot in a hyperplane, splitting those two groups. And then we can, once we fit that hyperplane, we collapse it back down into our 2-dimensional feature space, and we essentially drew a circle between these two groups. So everything on the inside is a yes, and everything on the no, on the outside is everything on the inside is a yes, and everything on the outside is a no, right? So there is a downside that it fails when there isn't a hyperplane that perfectly separates the two groups, but using these kernel tricks or these kernel extensions or kernel functions, we can essentially get around that issue. So that is the general idea behind support vector machines. One last thing I wanted to mention on the support vector machines is that if you recall to many, many slides ago, when we were looking at that scatter plot between interpretability and flexibility, we saw that support vector machines was down at the bottom right-hand side. So it was a very flexible method, but it wasn't that interpretable. And the reason is primarily because of these kernel functions, right? If we run this model, for example, well, that seems quite interpretable. Right, it's easy. Here's my plane, very intuitive. It's very interpretable. You can explain what's going on here. The lack of interpretability comes from adding those kernel functions, where it becomes harder and harder to explain what exactly the model is doing. So you get a lot of flexibility with these kernel functions, but you start to lose you start to, yes, lose your interpretability when you get into these more advanced kernel functions. So that is all for this lecture. On Friday, I believe you all will be learning about implementing these methods in R. I believe specifically you'll be running a lasso regression, a ridge regression, elastic net regression, and a support vector machine in R. Hope you all have a great rest of the week.